you hear me? Yeah, cool. Cool. So take two. I'm Alex. I'm a PhD student at Royal Holloway. I'm going to be talking about some joint work that I've been doing with Ian Goldberg, Nick Sullivan, George Tankersley, and Filippo Valsorda. And I'd also like to extend an honourable mention to Cecilia for making sure this talk went through. But yeah, so in this work, we're going to be analysing the effect that content delivery networks, or CDNs for short, have on creating accessibility problems for large subsets of users on the internet when browsing. So if you're not familiar with CDNs, we can think of them essentially as a reverse proxy for multiple websites that are customers of the CDN. And when a user wants to access a website that's a customer of that CDN, their request is sent through the CDN, and the CDN then handles that, grabs resources from the website, and then returns them to the user in the future. So why would a user use such a thing? Why wouldn't they just host their website themselves? Well, CDN can actually increase speed dramatically. So a CDN can geographically or globally distribute their website's data across the world, which brings the website closer to the user, makes the browsing experience much quicker without changing it in any way. And moreover, typically CDNs use caching optimizations to bring resources close to users without having to actually access these resources from the website. So there's another reason as well, and that's security. So a lot of CDNs market security as a big feature of their offering to customers. So when a malicious user comes along and sends a request, the CDN would block that request if a user is deemed to be malicious. But in this work, firstly we ask the question, how do CDNs deem users malicious? And secondly, we ask, does this have any negative impacts on honest users who are somehow deemed to be malicious as a false negative? So firstly, how do they do this? So typically, we're going to be using Cloudflare as a case study, so I'm going to be sticking close to the way they work. But a CDN uses IP reputation sometimes as a metric for distinguishing whether websites are malicious or not. An IP reputation, so a CDN will have IP addresses that are assigned reputations in some either public database or their own private database. And these reputations would demarcate whether the CDN allows requests through or whether something else happens. So if an IP address is deemed to have a good reputation, the user is deemed to be honest and the user gets the resource they requested. If an IP is somehow deemed to be malicious, if it's been associated with malicious behavior in the past, then the CDN may block the request or it may ask for some extra information before it processes it. So in terms of false negatives then, like I said, we're talking about users who have IP addresses that are deemed to be malicious, but they are honest users. And when might this happen? Well, maybe if you're using a static shared IP address, where one user on that IP address has committed some malicious activity in the past, then that user then all honest users who then further go on to use that IP address will then be assigned the same malicious IP. And if they then, so then if we talk about which affected users, we're talking about users tools like Tor, VPNs and I2P services, where the set of IPs is static and it's also very finite. And moreover, CDNs may do some very aggressive targeting where they just see IP addresses that are known to be, say, Tor IP addresses, and they may block them. And this is a huge issue, so the worst case is CDN may just completely block requests that come from these IP addresses, which it deems to be malicious. And obviously, we want to do everything we can to prevent this from happening, because users of Tor have very legitimate reasons for doing this, and if we block their internet access, or if we have private entities like CDNs blocking internet access for these users, then this can hugely harm user participation in the internet. In an average case solution, CDNs may ask for some sort of challenge to be filled out by users before they get in access to the resource. So this may take the form of a CAPTCHA, where the user has to solve that CAPTCHA in order to then receive the website resource they requested. And this may all seem well and good. It may seem like it solves the issue, but there are many issues with CAPTCHAs that I'm sure we all know. In the very weakest setting, CAPTCHAs are very annoying and slow to fill out. They're very hard for humans to fill out, which is obviously against what they stand for. And moreover, there are implementation issues and browser compatibility issues which can render these things as blocking as if the CDN was just completely blocking the request in the first place. So a possible solution to all of this is to say to the CDN, why don't you just not block any requests? And unfortunately, they have economic reasons, which means that they won't do this because they have customers who buy their product because of the security they offer. And the second solution, which Cloudflare, at least up until a few years ago, used, was to use these cookies that when a user answered a captcha correctly, they would receive a cookie back along with the resources, and then they would use that cookie in future requests to different domains. But the problem that this brings is it breaks the anonymity of the user. Even if they're using an anonymity tool like Tor, they can, Cloudflare, because they have a CDN with this overarching access, they can link requests across multiple domains, and this is obviously a terrible issue. So in this work, we develop an anonymous authentication protocol based on a cryptographic primitive known as a verifiable oblivious PRF, or pseudorandom function. And this combines some previous techniques used based on elliptic curves that I'll go into next. And the upshot of this is we implement this oblivious PRF protocol into a client-side browser extension and a server-side integration with Cloudflare that allows users who are deemed to be malicious to bypass Cloudflare challenges if they initially provide the proof that they are honest in some point in the past. And then we give a survey of our results of our deployment showing that we concretely bypass a number of challenges, which makes browsing much easier globally and for users of these anonymity tools I talked about. So for the protocol, if you're not familiar with an oblivious pseudorandom function, we have a client C and we have a PRF holder who is a server, and they have a key K. And the idea of this protocol is that the client wants to learn a PRF value at some input X, but the client doesn't want the server to learn the input X. So this bracketed notation means that the client sends some blinded input X, and the PRF holder can evaluate the PRF at that value X, but it does not learn the value X. And moreover, the client does not learn the PRF key K in the response. And then a verifiable oblivious PRF, we have the PRF output Y, and we have a proof pi that Y is indeed an evaluation of the PRF at the input X. And pi here is a non-interactive zero-knowledge proof. So how would we instantiate such a thing from elliptic curves? I'm simplifying slightly in the interest of time, but essentially the blinded input is some hashed value of X to an elliptic curve, and then blinded by some random exponent R, which is known to the client. And then the PRF value Y essentially raises this blinded input X to the server value, server key K. And then the client learns the PRF value by unblinding this input X by removing the exponent R. And then pi here is what is known as a discrete log equivalence proof, which I'm going to talk about in the next slide. So without getting into the cryptographic and mathematical construct of how these things work, essentially a DLEQ proof, or discrete log equivalence proof, shows that if a server commits to some pair G and H, where H is G risen to the power K, then any future pair X and Y, where Y is risen to the same power K, a DLEQ proof allows this entity to show that Y and H are risen to the same power K. Essentially, the upshot is that the server can prove that they use the same key K for each signing process, and we use this later. So for our anonymous authentication protocol, we haven't given any authentication mechanism yet. In fact, we give, and so now we talk about a signing and redemption phase of a protocol. So our signing phase looks very much like the verifiable oblivious PRF. The client sends its blinded input X and recovers a PRF value Y along with the proof, the DLEQ proof pi. And the client stores the unblinded input, and then in the future, when it wants to authenticate, it sends over the original unblinded value X along with some MAC keyed by the signed token that it received from the server. And then in order to authenticate, the server simply verifies the MAC by recomputing the signed token using its key K. And then this grants authentication. So we can do this for multiple tokens by the client sending over multiple tokens instead, and then the server sends back multiple PRF values, but we have an initial problem which is similar to an existing design whereby we have a DLEQ proof for each signed token Y. And this is cumbersome, it's difficult for deployment, and it's not very practical in terms of computation and communication. But we used existing results of Henry in his thesis of 2014 to batch this proof into one value that allows us to verify this proof for any polynomial number of tokens. And the key thing that we're trying to show with this protocol is that it's unlinkable. It preserves anonymity. So our definition of security, which we give in the paper, is that any signing phase from our protocol cannot be linked to any future redemption phase. And this is perfectly drawn from the fact that the client uses some random exponent R, which uniformly randomizes the token. A second property that we require is that the client cannot forge signed tokens. And we derive a reduction from the one-word decryption security of El Gamal to show that it's also difficult for the client in our protocol to forge a list of n+1 signed tokens from an initial list of n signed tokens. And then finally, we require this property known as key consistency. And what this shows is that a server cannot use different keys for each signing phase for one pair of commitments, G and H. And this is to prevent the server from using, in each signing phase, a different key pair, which would then lead to a de-anonymization attack in the future. So how does this fit with Privacy Pass, our browser extension? So Privacy Pass is a browser extension that we developed for Chrome and Firefox, and it also works for Tor browser. And in this section, we're going to talk about a particular case study that we did with Cloudflare in order to integrate this protocol between a client and a server. So Cloudflare, if you don't know, is a CDN that serves 10% of the internet's traffic, and it uses this IP reputation mechanism that I used before and uses captures to prevent malicious users from accessing resources. So how is Privacy Pass going to work with Cloudflare? So a user has a malicious IP and they visit a Cloudflare website and they get shown a captcha. And when the human user, fills out the captcha, Privacy Pass is going to inject some elliptic curve points, which are the blinded tokens I referred to before, into the HTTP response. Then Cloudflare, when it returns the resource, providing the captcha is answered correctly, it also signs these tokens, provides a DLEQ proof that these were signed with the key K. And providing this proof passes, the Privacy Pass stores these tokens for the future. So this is all happening in the browser without the user doing anything. Then in the future, when Privacy Pass has some stored tokens and you visit a Cloudflare website and Cloudflare wants to show you a captcha, instead of the captcha being shown to the human user, Privacy Pass overtakes the execution and presents one of the redemption phase from our protocol earlier, along with this MAC value and the unsigned token X. Cloudflare can verify the MAC by re-signing the token and then stores this X so it can't be used again in the future, and then grants access to the website for the user. We also provide a single domain cookie so that the user can then access the same domain without having to re-spend tokens on it. But this doesn't mean that this cannot be used for different domains. So this is how Privacy Pass grants access to web resources without having to show challenges to these users. So in terms of some specifics, I'm just going to talk about a couple of them. So for these public commitments, G and GK, GH, for the DLEQ verification, in order to do key rotation, these are currently baked into the extension, but these would have to be rotated when rotation happens, for when key rotation is required. And we incorporate quite a low bound of the maximum number of signed tokens, and this is to prevent clients from farming tokens. In order, if this number was too high, then the client may be able to build up a huge stockpile of tokens, and then be able to launch DDoS attacks that completely bypass Cloudflare's security mechanisms. So I've got some links here with some code. I'm also going to show them at the end. So, and in terms of how does Privacy Pass influence the browsing behavior of the user, so the signing phase can be regarded as slightly burdensome in the sense that it adds some noticeable extra time to the browsing behavior when a captcha is being filled out. So from the start to when the user receives the signed tokens, for the canonically signed number of tokens, which is 30, we add about 3 seconds to the browsing behavior. But for redemption requests which come afterwards, these are very fast, and we completely eradicate the need to fill out captchas in the future, which were required before. So we have a slightly burdensome signing phase, and then we have much quicker redemption phases afterwards. So we regard this as an improvement on the existing design. In terms of request sizes, again, we have to add these elliptic curve points to our HTTP responses, so they grow slightly, but it's not going to be anything that changes dramatically the user browsing experience. And again, redemption requests are very, very small. So the release of Privacy Pass was in November last year, 2017, and by the end of that month, we had over 11,000 downloads across both Firefox and Chrome. And then again, this month, we've had since then, we've grown to over 75,000 users, so we're really happy about this. In terms of the metrics of the deployment, so you can see here in the first pink line that Tor users are, as I speculated before, they're dramatically targeted by these challenge mechanisms that Cloudflare use. In terms of redemption, so when tokens are being signed to bypass captures, you can see that these are growing since the deployment, and each one of these constitutes a capture that's bypassed, and then the single domain cookie numbers allow us to further bypass captures at the same domain. So we're seeing a dramatic reduction in the number of captures that Cloudflare are having to serve to users. And moreover, and so hopefully we can reduce these percentages by something close to a factor of n, providing everything optimal works. So in summary, privacy pass is very much, we believe it's still very in beta, so that goes to the protocol and the extension itself, and we would really welcome anyone who has any ideas regarding cryptanalysis to get in touch with us. I have some links here, and hopefully if the slides are online later, you can speak to me and I'll give you them. And please, if you're interested in contributing, then get in touch. And then final notes, I've missed a lot of stuff out from the paper, so there are many more out-of-bound attacks that I haven't covered, along with comparison with existing research into anonymous eCache and privacy-preserving blacklisting and whitelisting, along with the security proofs and implementation details. And finally, we're currently working on IETF standardization of our ECVO PRF protocol that we hope to materialize soon. And then for future work, we're updating Privacy Pass all the time. We're working on integration with more capture providers such as Fund Capture, and also cryptographically we're trying to move towards post-quantum solutions if possible. But yeah, thank you for listening.
All right, so I think we can take maybe 2 or 3 questions, but there is a break coming up, so after that, maybe you can take your questions offline.
I was wondering how you prevent double spending or replaying a token.
Yeah, so I didn't cover this explicitly in talk, but so when a token is spent in the redemption phase by Privacy Pass, Cloudflare stores that, and we currently have a Bloom filter sort of structure that Cloudflare has in its edge, that when these tokens are spent, Cloudflare can then check in this Bloom filter that the tokens exist before it verifies the connection. So that's how we currently verify double spending.
How do you prevent that from growing forever?
It's a good question. Currently, the resources that Cloudflare have mean that we don't have that issue. But yeah, it's a valid question. I think when we do key rotation, we'd have to rotate. It's very unlikely that tokens are going to be reused after key rotation, so we'd rotate the data structure then.
I have a sort of a 2-part question, but it's really the same question. The question is there any data about the actually malicious traffic, and if they've switched to using this rather than solving CAPTCHAs? And more specifically, last time I checked a few years ago, I think it was a little less than 1 cent to solve a Cloudflare CAPTCHA from a CAPTCHA farm. And I was wondering if you have any data about if that, if you get 300 tokens per CAPTCHA solving, has the price gone down to a 300th of a cent, or is this, have the malicious actors actually adopted this system?
So for the second question, we don't have any data on the economics of CAPTCHA solving. But yeah, this increases the utility of CAPTCHA solving if you can get those, if you can pay for that. For the first question, can you remind me, sorry? If
Cloudflare has told you if there's actually been a lot of malicious traffic using this.
So the numbers we're seeing is that there are still, it's relatively small, the number of people using Privacy Pass. So we're not seeing a drastic increase in the number of people using. I think if we were seeing malicious traffic, we'd likely be seeing many tokens being spent in minutes and seconds, and we're not seeing that. It's usually dragged out over an hour or so. So I don't think so, but I haven't got explicit numbers.
All right, I think Jeff will be our last question, and then others will have to take them offline.
Okay, so the DLEQ proofs show that all the keys used in a particular in answering a particular session are the same. But is there some CA scheme or certificate transparency scheme or something backing up that these are the same, that these Ks are the same for all users all the time? Is there anything?
So these commitments are currently they are baked into the extension code. So these do not change, and so these have to be used with the DLEQ proof verification. So.
Okay, so thank Alex again, please.